Okay, let's see. Check if it's actually correct branch. Okay, yeah.
Okay. So what is this now showing?
Yeah, so this is a new format of the evolution object. So it basically is now event-based. So we have inputs and outputs for each event, generations for each event, and the rule that's used.
Okay, so the input and output, those are labeling hyperedges, yes? The indices.
Yeah, and the
label
hyperedges are from this list.
So those are, so the numbers in that list are elements,
Yeah.
not hyperedges. Okay. So then, what is the -2 in the rules?
Oh, that's just, it's just a pattern.
Okay.
Yeah, I copied it from C++ code, that's why it's in this format.
And the minuses mean non-literals or something?
Yeah, it means patterns.
Okay. Okay, okay. So let's think about this for a second. So what this is doing then is it's saying, given these events, okay, so the event inputs are, that's a, I'm now a little confused.
Yeah, this is initial event.
Yep.
For convenience here, because no inputs and output is a whole initial state.
Wait a minute. So the output, hold on. So each event records its edge IDs that are involved, but each event should follow the pattern of the rule.
Yeah.
So I don't understand. Oh, the creator, the initial event.
That's initial event. It's special.
Which you haven't shown here. So the subsequent events.
No, I did show it here. That's what it is.
No, I understand, but you didn't show it in the rules. You didn't show an initialization rule.
Yeah.
Right. So okay. So the subsequent events are all of the form one singleton and double goes to something. Okay.
Yeah.
So then. So those are the event inputs. I don't understand why.
So 1, 2 refers to these two edges.
Yes. Okay, so why are there, in the event outputs, there are singleton edges?
Because a single edge.
Because there's a single edge there. Okay, all right, I understand.
So it basically starts with two unary edges at the ends, and it moves them along the edges. Okay,
so are you showing here, is this, what is this picture? Is this the generations?
This is states list by event. So it's one event at a time. So you can see one of them, and as it moves, it deletes the edge it moved through, because otherwise it's just going to keep repeating and will grow very fast.
But hold on a second. But there isn't a unique evolution this way. There are many branches, right?
There is a unique evolution up to here where it fails because there are multiple destroyer events.
Okay, fine. So I mean, most of the time, there will not be a unique evolution in this picture, right? So the question is, how do we represent that? And what you're saying is, in this picture, this is essentially the multi-way graph. This picture is going to turn into the multi-way graph because every one of these, the step from one thing to the next is an edge, right? And in this case, it's just the partition 2-1 of this thing gives the edges, yes? But that's not going to be generally true, right? So this thing turns into the multi-way graph, right? And these are the nodes of the multi-way graph.
So
everything you're showing here.
It's it's not a complete global multi-way graph because it doesn't have duplicates for space-like events.
Walk me through that again. Hold on a second. So you're
saying, like you see, for example, here there are two choices of which particle to move. But from the point of view of local multi-way system, it doesn't matter which order they're used in. So there's only one path here, whereas in the global multi-way system, there would be branching.
Well, okay, but if you want to get the path weights right, you're going to have to account for that. Well, there are multiple matches that are possible.
Well, yeah, but they're independent.
So what? I mean, in our theory for what the path weights do, you're going to have to account for path weights. I mean, you should just keep
Well,
track
do
of
we
the
know
path.
that it's the right way to account for path weights?
No, not for sure, but it's a reasonable guess.
Well, because again, it seems like it's a global operation to account for path weights this way, because weights, in one side of the system would depend on the other side of the system.
No, but you know, when you're doing this rewrite, you know your code certainly knows you saw two different collections of edges that could both be rewritten in this way, right? Am I confusing
yes,
myself?
it does know that.
Okay, so I'm just saying, keep track of that. I don't yet know why it's going to be important, but I would keep track of that.
Well,
okay, so
let's see. Well, it does keep track of that in a sense that from initial event, we are going to have two events coming out of it in the causal graph.
Okay.
I'm not sure if causal graphs work. They probably don't. No. But let's see. And we can make one very quickly.
What are you trying to do?
Well, I need to label that these are edges.
Yes.
Right.
What does the arrow 1 mean there?
These are events. Oh, yes. It's better. And we just need to have the same thing going the other direction.
Okay, so then you're knitting those together by edges.
Yeah. Which you could, well, I think it's actually useful to see because it makes it obvious where the branching happens.
I wonder if we should have a second argument to catenate that does that.
Okay, what does that mean? Okay, we really need to distinguish them. Actually, hold on. Style. That.
Okay, let's see what's
Yeah,
happening
so
here.
you can tell the two events simultaneously happen because well, if you look at this layer, they
Okay,
both
hold on.
depend on
Hold
the
on,
initial
hold on,
condition.
hold on, hold on. Okay, so there's an initial condition there that has certain edges. Then pairs of those edges are used by the events. And that event, so event 1 is producing a single edge 8. Right?
Yeah.
Oh, this is nice. Okay, can we run a oh my gosh. Just for fun, let's take this and let's run a more realistic, let's run of the rules that we've studied before. So
Okay, let me just
why don't you
package
package that? Yeah.
Advantage graph.
I like this way of showing, you know, edges turn into event. I mean, this is basically the evolution events graph, but shown at the level of individual edges.
Yeah, exactly. And what nice about it is you can see, for example, because the two edges coming out of this, well, two causal edges coming out of this edge,
Yeah.
you can see the branch like.
Yes. Oh my gosh.
Well, okay, let's get another rule.
Let's look at the let's look for a rule that we've studied before. Let's look for one that just hold on, let me find one. I mean, why don't we take our
We have a random button.
okay, but some of them will be very complicated. But I would take, yeah, all right, okay, fine, take that one. But doesn't it click to copy? Oh.
Let's see.
Really, you can do that? I would just go a couple of steps there.
Okay. I mean, I was just simply.
You know what? Why don't we use our most favorite rule? Let me just put that in the Zoom chat, just because it's like that, but it's.
No, the evolution is fast. I mean, it's still linear, the number of events.
Right. Oops. Okay. Let me hold on. Let me just. Here, I'll send you the rule. This rule here.
Okay.
And that's okay. Self loop.
Okay, so I need to deal with options.
Okay, let's do a layered graph on that. Okay, let's say aspect ratio of the layered graph arrow half or something. Okay, let me understand this picture. So each successive level shows either events or edges, right?
Well, I'm not sure what's because it's not a correct layering necessarily.
I see. So you
Actually,
could make.
We need to make them larger so you can see something.
Three. Okay, so in fact it did do that. Yeah. It did do that. Okay, let's think about this
And
for
you
a
can
second.
see there are lots of branching going on.
Yes. And lots of merging. Right? There's lots of branching and lots of merging. I think, unless I'm reading this wrong, looks like it to
Let's see,
me.
where is the merging?
All over the place, where those things are going into the same events. So at every step,
yeah,
every event is generating separate edges, right? So things come into, so what's happening is the events collect together multiple edges as they do. That's what an event does.
yeah.
So then, let's take a look. Hold on one second. Let me give you another rule to look at. Okay, I'm going to give you another rule in the chat here. Okay, there you go. Another rule in the chat.
Oh, but that one is not multi-way. It would, I mean, it's supposed to do exactly the same thing. And actually, let's verify that.
Yeah,
If
keep
I
it run longer.
Global space. Yeah, see, it does exactly the same thing.
Okay. So run it like 5 steps. Okay, great. Okay, so let me just understand what's going on here. So this never collects edges into the same event. It never collects space-like separated edges into the same event. It never collects separated edges into the same event.
Yeah.
Okay, great. All right, so that, okay, let me look at the next one then. Okay, here we go. Here's one. All right, let me send you another one. Okay, try this one.
Okay.
Interesting. Okay, so that purports to be a causal invariant rule in some way.
Well, right.
How do we see that here? I think.
Okay, so edges are blue. So we have this edge, it's split into branches. And now there's hold on. Well, it splits into branches, but it does the same way.
But why is there an edge that isn't used?
Okay, so one point I need to make is that it does not do any deduplication at all, which means if there are two identical edges, there are always two ways to merge them.
Mm-hmm.
So it would actually duplicate those two ways, which I suspect is what's happening here.
Right, fine. So those are the two ways round. That's the path counting that we would otherwise conflate, but we're not conflating here. But what's that leftover edge? See what I'm saying? So like, for example.
Yeah, I see.
Okay, so like let's take the event.
Well, it's one of the edges that was never used.
No, I understand that.
3 edges.
I understand, but so what feature can we? Why don't we display this for just 2 steps, but give us the whole output, not just the color? Don't change that one. Don't change that one. Leave that one. Leave the 5. Okay, now. Okay, so now let's just do. Can we label the edges? Can we say vertex labels?
Right, and then we need
That's
to
not very useful.
Well, we need to figure what they are. So this is edge 8, which is
just use the
1, 3 here.
Okay, so it never has a friend. It never has an identical friend.
Yeah.
Okay, let's go back to the previous picture. Let's try to understand the previous picture. So whenever there are two identical edges produced, they're the ones that have that little twisty tie that happens, right? But there are a bunch of edges produced that never have a pair, never pair with anything. As soon as they pair, they make that twisty tie with a little tuft on the side that never pairs, right?
Yeah.
Okay, so what is going on here? Let's try one other rule, okay? I've got another one for you to try.
Okay.
Go ahead and try this one. I would try just a couple of steps. That's going to be very complicated.
Ah, okay, it crashed, which is not a good sign.
Particularly bad if it was the actual universe running. That would be like, is that it? Huh.
Well, 2 steps.
Yeah, I understand. Huh. Hold on. Okay, could you run that guy just a little bit longer, like 3 steps?
Yep, this substep takes a while for some reason.
Well, it might get pretty big.
And it crashes when I try to abort it, which...
Okay, well, that's the way it works. But try running it again with just 2.
Okay, let me just... I need to write it down. So don't forget to look at it. Okay. Okay, so 30 events for 2. Let me just check out. Well, it does have at least 500 events.
Okay. Well, let's just regenerate it for 2, please, so we can see that. Okay. All right.
Wait, we can generate part of it.
No, I understand. I understand. That would be useful.
Similar.
It would be useful to do that.
Let's say 100 first. Wait, what happened here?
Try 200. Okay. All right. So somewhere, where will it be likely to be not sort of, I mean, can we tell where it didn't get to from this picture? Probably not really.
Well, yeah, that's what I'm trying to figure out. Yeah, it's weird. It looks so uniform.
I know, but it just doesn't. You know, it could just be one of those. Look, why don't we just do this and then do 220 events? Copy that down and then do 220 events. Okay, now make it bigger and let's take a look at them. Yeah, look at that guy on the right that was a non-connector. It now connected.
Okay, I see.
Okay. Okay. All right, let's back up and let's take a look at this thing with the 2-step case for a second. So that is doing a 2-generation. Is that correct? Is that a 2-generation evolution? Yeah. By which we mean
1 and 2.
Tagged. A generation means it never reuses in a time-like way, and it can reuse.
No, it does reuse in time-like way.
No. It doesn't reuse the same. Once on that generation, something was produced, right? That is indicated as over for that generation, right? So it doesn't go back. It doesn't rerun. It just produces a bunch of edges on that generation. From what it sees what it has at that generation, it produces a bunch of new edges. But the edges that it produces,
no, it can reuse edges from previous generations as well.
No, I understand that. I understand it can reuse the edges from previous generation, but it cannot reuse the edges from this generation. In other words, it's just doing,
well, yeah,
kind of doing the analog of a cellular automaton thing, where it's just using all previous values, but not using any of the current values. Right? That's the definition of your generations. Okay. So the question here is, how do we indicate from this? So this is, so just for my understanding, the multi-way graph we should be able to get by simply eliding out the event layers here. The ordinary multi-way graph just comes by eliding the event layers. Correct?
Well, to get ordinary multi-way, we need to reconstruct the states themselves. Which is not, well, it's very complicated because normal, I mean, a global multi-way graph assumes the only space-like matches.
Oh, I know. But I mean, we can make another kind of multi-way graph here by just eliding the events.
By doing what with events?
Elide the events, get rid of the events. I mean, so hold on a second. Within each, I see, these are individual edges. These are not, this is what I'm getting confused by. These are individual edges.
Yeah.
So this is kind of a micro multi-way graph. The events are born local in the sense that an event is always a local thing.
Yeah.
But an edge here, these are, the edges are born local too. I mean, the edges are local by definition. The issue is to make an instantaneous version of space, we need to knit together edges.
Right. So, I mean, first of all, we can still have a foliation of this in a straightforward way, but it would not give us just, it would give us branch-like pairs of edges as well.
Okay, hold on. So what we're trying to find is an anti-chain of those edges which do not, what is the definition of what would be a decent spatial section, so to speak? Do you see the question? I mean, that is...
So the best way to determine it I have right now is you take a pair of edges, you compute the past for one of them, and then you start computing the past from another one, and you see at which kind of object it intersects the other past. If it intersects at an event, that means the space-like, at least in that area. But so, in other words, if it only intersects by events everywhere, it doesn't intersect, then the space-like. If it intersects by an edge, it means at least one of the edges had to be reduced to produce. Had to be reused to produce them. So they're at least partially branch-like.
Okay, hold on. Let me walk through that for a second. Okay, so given an edge.
Actually, there are examples in the bullets in the we can look at.
Okay.
For trivial cases. Okay, let's see. Yeah, this is well, this is a non-trivial. Well, it's a simplest non-trivial case. So the question is, what is the separation between VF1 and VF2?
V is a vertex, or what? What is V?
Oh, the VF1 is the name of the vertex. Oh,
Okay.
well, it's hold on. Well, it's the name of an edge, but they're pattern rules. So anyway, they're just explicitly named edges.
I think we should go back to the other picture for a second. Can we go back to the other picture? I think it's going to be easier to understand. Okay. So, okay, there was an initial event. The initial event, so that initial event is the beginning of the universe, and it generated two self loops. And those two self loops are the edges that we see on the two sides there, right?
Yeah.
Okay. So those two self loops had a way to be used immediately to apply the actual event there to generate, in each case, a triple of edges. Now, I'm a little bit confused. Oh, I see. Each of those events generates a triple of edges.
Right.
Right? Okay. Meanwhile, those edges were not consumed by those events. They were left hanging around. Right?
Yeah.
So then, at the next step here, there is a way to take a newly created edge and make an event with a previously existing edge.
Right, like this one.
Okay. Yep. Okay. So let's understand what really happened. What's happening there? So now the point is that what we want is to know. Okay. So we have a time-like sequence here of from a particular edge. So a little weird here that one of these edges, there's a time-like sequence that reuses that edge, right? So if we look, on the left hand, one of the first two edges goes through an event, then it produces an edge, then look all the way to the left, the original edge, and it's incestuous. Its children, it's mating with its children again, right?
Right. So it matches time-like edges as well.
Well, I'm not sure I would necessarily put it that way, but I mean, basically, okay, so it can...
Well, these two edges are time-like because you can get from one to another.
Yes, I know, but when you say matches, I'm not sure, there's no matching.
There is matching of vertices.
No, I understand that, but those edges, which edge are you indicating as time-like?
Well, for example, this one and this one.
No, wait a second. What do you mean? Are we talking about the hyper edges, or are we talking about the edges in this evolution events graph?
Oh, the hyper edges. The vertices.
Wait a minute. You're saying that an event that is created contains two vertices that are time-like related to each other.
Yeah.
As in, okay. So what that means is that vertex is collected in a hyperedge, and then, okay, let's understand what it really means. So it's collected in that hyperedge, and then it is, by time-like, we mean that the two vertices, the two elements collected in the hyperedge are incestuous, so to speak. One of them was the progeny of another. Is of the other, right?
Yeah.
That's what that means. Okay. So, and space-like in that sense means Okay, so the definition then, time-like means one of them was generated, that within that hyperedge are things which were generated at different stages in a single hyperedge. So in the previous global approach, a single hyperedge is destroyed, boom, and a new hyperedge is created. In this case, the hyperedge can make use of things that were in previous hyperedges that were in its past.
Right.
Okay, so let's understand what it means to be space-like, a space-like edge. So, okay, so a time-like edge, it makes use of things that were in its past, of things contained in edges that were in its past.
Right.
Okay, so a space-like one is...
Well, so definition is so the branch-like one would be the one that cannot be produced if we... Well, it cannot be produced in any evolution order of global space-like system.
Let me understand that. You're saying that a branch-like edge has the feature that it must come, there is no way, okay, so a space-like edge is one where the two pieces, the things in the edge are never time-like. But that's a definition of either space-like or branch-like.
Yeah.
So now the question is, what is the definition of branch-like? And that is...
Yeah, so if we run all possible global space-like systems, we will produce all space-like edges, but not...
How do we define a space-like system?
Well, it's just a Wolfram model as the previous was. That it deletes edges after it uses them. So more specifically, a pair of branch-like edges cannot coexist in a global space-like system.
Yes, right.
And
in the way
to be clear, the way I can identify whether they're the same or not is because, I mean, it's essentially blockchain. Each vertex and edge have an ID, which is preserved for different evolution orders.
I didn't understand that comment. Let me understand that comment. So in this picture, hold on.
Yeah, so I was comparing edges in different evolutions, which is not, I mean, it's not trivial that it can be done. But I'm saying it can be done because we can assign a unique ID for each edge and vertex based on its history.
Sure. Okay, so if we do that, then what you're saying is, I don't understand what you're saying. So you're saying, given essentially a Git history here, in which every node, every edge here knows its complete lineage. So what?
Right.
Okay, so every edge knows its lineage, and then it looks at its lineage. I'm confused here. I think
No,
the issue
here is a absolutely inefficient way to do it. So let's generate all possible evolution orders for the global space-like systems.
Yeah.
And then in a match all system, we take a pair of edges and we find for each global space-like system, we see if both of them appear in the same one or not.
Sure.
If there exists a system where both of them appear, then they're space-like.
Right. Okay, let me try to understand that more clearly. Okay, so, I mean, that's saying, does there exist, that's space-like bifoliation, basically. So each one of those, what you're saying is you choose all possible event selection orders, event selection functions,
event ordering functions.
Yeah. And you ask the question, is there a way of generating a total order so there are many potential, okay, so let's look at this here, and let's look at the events here, okay? So one question is, what are the possible total orders of the events, right? Consistent with this local multi-way system.
Yeah.
Right? So we imagine all those total orders. For each total order, we can ask the question.
Well, it's not total orders of this system because it branches. It's a total order of systems that don't branch.
Let's think about that. So you're saying, okay, but a total order of this system will be, that's perfectly meaningful, but some parts of it will factor out because they were branched. You can make a total order, it's just some parts of the total order will factor off, right? Because it doesn't matter. The issue is
factor. I mean, what we're trying to do is determine whether the two edges exist simultaneously in a system or not. So we have to look at systems which don't branch. Otherwise, how are we going to tell if?
No, I understand. I understand. So I'm saying that if we look at, well, you're saying, okay, one way to do it, I'm now very confused. I mean, if you make, okay, let's just understand formally from this picture that you have down there, okay? Let's indicate which things can be space-like separated, which things are definitively branch-like separated.
Okay, let's see. Well, so the first two obviously are space-like separated because they're produced by the same event.
Okay, let's think about that statement for a second. Okay, so what's the generalization? So okay, let's keep going then.
So,
okay.
Yeah. Okay, let's see.
So first statement is, everything, all edges produced by a single event can be viewed as space-like separated.
Yeah. Oh, okay. Actually, my previous definition was not correct. Because here's why. We can have... So one thing that can happen is that the rule can match a branch-like pair of states and produce multiple outputs. So those outputs are space-like, even though they're not possible in the global space-like system.
Mm-hmm.
And those, I mean, presumably those just correspond to classical states that can only be obtained as a result of quantum effects.
Yes. All right, let's walk through this again, okay? What it means to be space-like, okay?
Yeah.
Okay, first question is, where is the light cone? Where is the spatial light cone? Draw spatial light cones here. Because for things to be space-like separated, they have to be outside of the spatial light cone of some event, right? Outside of the light cone of an event. If two things are going to be space-like separated, if two
fair enough.
events are going to be space-like separated, they better be outside the light cone of those events.
Yeah, well, if there is a light cone, then time-like.
Indeed. So for every event, it's pretty straightforward to determine what is in its light cone, right? Its future light cone.
Yeah.
Okay.
So. Well, yeah, future past light cone.
Right. So okay. So then, what we want to do is look at those future light cones and ask the question, let's see. So it is those events. So if we want to tag who's space-like with respect to who, right? Isn't it the case that we simply have to say whether those light cones intersect?
Well, no,
No,
because they
that's
can
not right.
intersect
That's not
at an
right.
edge.
Well, they can intersect in the future as well. No, but I'm saying event to event.
Wait, in the future, that's okay. That's I don't understand how to think about it in the future.
What's that?
Why? I mean, I think we need to look at the past, not at the future.
Yes, fair enough. Okay. All right.
So if in the past the light cones intersect at an edge, that means the same edge was used multiple times in different events, and the result of that is the pair of edges we're looking here. So that would imply they're branch-like.
Indeed.
At least partially.
Right. So okay. So let's. Okay. So the question is the past light cone of an event, right? We look at the past light cone of an event, and we ask for two events. If those past light cones are disjoint, then
they did well. Then that means they intersect at the initial event, which makes them space-like.
okay, hold on. The definition of space-like is that they don't intersect. Those two past light cones. Is that right?
No, they can intersect. If they intersect at an event, that would mean space-like.
Okay.
Because if one event produces multiple edges, they're space-like with one another.
But we're looking at the event to event. So we could make a joint past light cone that involves both events and edges.
Yeah.
Okay, so what are you saying? You're saying we look at whether the intersection of the joint past light cone of two events, or two edges for that matter, they both have past light cones. So let's consider.
Yeah, we are looking at the edge of the intersection.
Wait a second. Wait. So,
okay, we use the word edge in too many ways.
Right.
I said we are looking at the boundary of the intersection.
Okay, let's define. Okay, given two events, we have a bucket of edges and a bucket of events that are in their past light cones, right?
Yeah.
Okay, so we can ask the question, what intersects in their past light cones? Now, eventually, their past light cones have to intersect at the initialization event.
Right.
Right? But now, as we go backwards, what does it mean if their first intersection is at an edge? What does it mean if their first intersection is at an event?
Right.
Right, so if their first intersection,
there might be multiple points of intersection.
I know that. So if their first intersection is at an edge, that means that those events are branch-like separated. Right?
Right.
If their first intersection is an event. I mean, sorry,
an edge.
And
yeah.
if their first intersection is an edge, they are branch-like separated for sure.
Right.
Okay. If, on the other hand, their first intersection is an event, I think then they're space-like separated, aren't they?
Yeah, pretty much.
Okay, so we go backwards and we ask, is their first point of contact? So I wonder if this is a correct criterion. So the statement would be their first predecessor point of contact is an edge versus their first predecessor point of contact is an event. Now, clearly, well, I don't think they can have both of those just because of the way
they can. This is an example of that.
I see. So there's a single, no, wait a minute, but an event is always connected to an edge, and an edge is always connected to an event. So I don't know how you're counting. See what I'm saying? So go back to the other picture. So you're saying that there can be something, an event is always joined to an edge, and an edge to an event. They go in layers, right? So in what sense can it be the case that the predecessor of an event, the predecessor of two events, you claim?
Okay, can I try to produce a modern version of this picture?
Yeah.
Maybe it would. Not sure if it will work. It did work.
Okay.
So let's see which one we're looking at. Oh, I guess this one is this one.
So what are you claiming here? You're claiming that the predecessor of those two, so it looks to me like the predecessors of those two meet in an event. But
it does look.
wait.
Like
yeah, hold on. Okay, yeah, I think so.
Let's see. So they can meet here. Let's see. It doesn't show what it was supposed to show. Can it investigate that? The idea is they use some of the. Well, you see the point here is that they both use V2. Yeah, I don't understand it. And besides, these are events.
I'm confused by your picture on the other thing. So hold on. Let's just take a look at what's going on here. So I don't understand what the VI1 whatever, but doesn't really matter.
I see why. Because I'm not. I need to actually specify event selection. It was not doing the multi-way. Okay. Now it's better.
Okay.
Yeah. So if you look at these two red events, then
yes,
they intersect by event here, but they intersect by an edge here.
Hold on. Let me understand this. Beautiful. Yes. Okay. Great. Good example. Okay. So that's a case where the most immediate predecessor, so in the case where they're coming from an edge, that's a branch-like separation. In the case where they're coming from an event, that's a space-like separation. So
Yeah.
Mixed branch-like, space-like separated pair of events.
Right.
Beautiful. Okay, and the definition of time-like is that what's the definition of time-like in this thing? So two events are time-like.
I mean, say intersect by each other.
Well, let's walk that through more carefully. So it's clear what it means. So that it means that if you go backwards, that in that past light cone is the other event. Right? So otherwise, it's you go backwards and you see, do you intersect in an event or an edge? That's very nice. Very nice. Okay, let me think about this for a second. So then if we look at that picture down below, so the events here are always, so all these events, am I mistaken, are branch-like separated, he says. Is that true? all these events have their predecessor, their predecessor intersection is always an edge, looks like. So I wonder if we can find one where that's not always the case. Let's look at our original example, the one that we've used as an example many times. Where was it? Is it that one? Yes, it's that one. Okay, that's a bit of a mess. Oh, I see. So we want to look at two events in the forest down there. And we want to ask the question, so one thing we should do, for every pair of events, this criterion, and every pair of edges, this criterion, what does it even mean? Wait a minute. Is there a notion of space-like separation for a pair of edges? Not really.
Oh yeah, it's the same as separation of the creator events. Unless it's the same event. Well, yeah, I think it's not exactly the same way for edges and events.
You're saying it does work the same way?
Yeah.
Let me understand that. So given two edges, I see, it's just a question of were they created as separate branches or were they created in separate places?
Yeah.
Okay. Okay. All right. Okay, I get it. So now, okay. So then, let me think here. So if we had a criterion for every pair of events and/or every pair of edges, what does it mean? Okay, so if we have pairs of edges that were space-like separated, that will allow us to draw, if we could find a maximal set of space-like separated edges. So for the edges, we'll have a bunch of pairwise comparisons. For every pair of edges, we can answer the question, is this pair of edges, space-like, time-like, branch-like, right?
Yeah.
Now, in the future, when we do go ruleal, we'll also have a rule-like separation, but that's a different issue, right? We could also have yet another notion of rule-like separated, because what that is we can define, we can basically have some kind of switch the rule.
But they intersect at an edge, but events they come from use different rules.
Yeah, correspond to different rules.
Which is a special case of branch-like separation.
Yes. Right. Which is what it should be. The ruleal multi-way graph is just an example of a multi-way graph.
Yeah. The way I understand it, ruleal space is just a normal space, but with large number of rules in the system.
Indeed, indeed. So this question of rule-like separation is just a question of whether the event on which two edges, no, I'm not getting this yet. Each event can be colored by which rule it came from. Right? I see. Right. I see. So the question is, it's rule-like separated if when you do the parsed light cone, you end up in a situation where there are two different rule events that come from one edge.
Yeah.
But then what is the exact criterion? Well, actually, look, forget rule-like separation. We can clearly do it. Okay, so let's just look at, okay, so for every pair of edges in the whole system, there is a comparator that says branch-like, well, it's going to actually say two things. It could say two things. It could say it's branch-like separated, and the first common, it took such and such a number of steps to get to the common ancestor, right?
Yeah. So well, it could, well, more explicitly, it would return a list of intersection points, and for each of them it will say what object is it.
Yes, but that list of intersection points will get very long very quickly. I mean, the first intersection point is the one of most interest, probably.
Well, not necessarily, because the first one is space-like, but they're also branch-like points. You want to know about that.
Okay, but so the branchial graph, as we've drawn it so far, is a first approximation to this, in which we're simply asking, is their first back intersection a branch-like, does it correspond to branch-like intersection? So
does it actually require branch-like intersection, or just any intersection?
I'm not sure. I'm not sure in this interpretation, but I think that, so in this case, what you've got, okay, so you've got a bucket of edges, and for every pair of edges, we say, are they space-like or branch-like separated, or time-like separated? Okay, so if we want to draw a spatial slice associated with a given edge, so we say, we've got an edge, and we want to draw its spatial slice. Okay, so first thing we do is we throw out everything which is time-like separated, because it's not in the spatial slice, right?
Yeah, well, and branch-like separated.
Well, and pure branch-like separated, yes. But if it's both space-like and branch-like, that's the case of a multi-space tower.
Wait, is it?
I think so. I think if it's both branch-like and space-like, that means it could be
I saw multi-space tower includes all branch-like separation as well.
It does.
Ones.
It does. But okay, but let's try to think how we would reconstruct one current moment of space, right? So we've still got way too many edges, because we've got...
Yeah, because they can be branch-like with each other, or time-like with each other.
Wait a minute. So we've got pairwise where we know they're this or that. But the problem is we don't know for the whole, so to make this maximal antichain or something, to make an antichain, we have to know for the whole, okay, for everything there's a pairwise version, right? So we can imagine growing a space by looking for everybody who is, so we'll have a recursive algorithm basically that tries to grow a plausible space-like slice.
Okay, hold on. Let's take all these edges and make a graph out of them. And we have an edge in that graph is a space-like separated.
Exactly. Yes.
Then if we have clicks in that graph, that's our space, basically.
Let's look at that. Let's look at that for one of these cases, right? So we should, okay, so you're saying no, I don't think it needs a click. So you're saying
well, if it's not a click, it means a pair of edges in that group are not space-like, so they cannot belong to the same space.
All right. Okay, so you're saying, well, okay, so we should try to draw this, and all right, so the relationship is, that's the graph of space-like separated edges that corresponds to, so if we take this original graph, that is those edges whose previous intersection is an event, right? How can that I bet there's some graph theoretic way to just see directly how to get that pairwise. So it's some kind of dual of this graph, something like that, not quite.
Well, I would be very interested to know what that algorithm is.
Which algorithm?
Of quickly determine whether the space lag or not.
Well, I mean, look, you got to reconstruct those past light cones.
Well, no, I know what naive algorithm is, which will do it in linear time for each pair.
Hold on. Let's say we use, what are those things called? Not Bloom filters, but the thing where you have bit fields. You know, you could determine it as a practical matter, could you not? By storing, I mean, essentially what you're trying to do is determine for every, is there some fast algorithm for doing this? You want to know, for each thing, you store its past light cone. Let's imagine you have a bit field that is its past light cone, right? That is a specification of its past light cone. Then all you need to do to understand, you need to know, you know, you're bit anding those things to find out where it intersects.
Oh, but it has quadratic space complexity.
Yes. Okay, hold on. Maybe there's a way to do this with high probability with hashing. How do Bloom filters work? Don't they do something like this?
I don't really know.
Well, anyway, so look, there's an algorithmic question of how best to do this. But I think definition-wise, this is a good definition, very good definition, actually, very clean. Right? So in this graph, which we can call, you know, the edge event graph, right? This thing you just drew is essentially an edge event graph.
Right.
And so the question is, from the edge event graph, there are many. So this graph immediately gives us the multi-way causal graph, right? Just by connecting, just by the way that we just elide out the edges and we've got relationships between events, correct?
Yeah.
Okay, so the test, so a couple of different things. The test of causal invariance can be made, I claim, in the events graph. And what exactly is the statement? The statement is ultimately going to be, what the heck is the statement in terms of events? I mean, eventually the statement is that the events graph consists of...
I think if we just have events graph, we lose information. Because we don't know anymore whether there's a branch-like or separation or not.
Mm-hmm.
Or it's just a different, more complicated event.
I see. Okay, so let's look then at let's look at this graph and ask the question, how do we test for causal invariance in this graph? Right, what does causal invariance mean? It means that branch-like separation will eventually merge. Okay,
well,
so
we can test that. So every time we branch from an edge, we draw the future light cones and we see the intersection.
Yes. Right. So let's understand what that means. So that means that the branch-like, two events are branch-like separated, or two objects are branch-like separated if their predecessor was an edge, if their common predecessor was an edge. Correct?
Yeah.
Okay. So now those branch-like separated things, we must ask the question, do their future light cones intersect?
Right.
In what? Does it matter? So do they have to intersect in an edge?
Oh, that's an interesting question. So, okay, I see what it means. So if they intersect at an event, it means that event just used both of them.
Right.
Oh, actually, one important thing to point out is that this merging is different from global multi-way merging as we had it in manual system, because there we do isomorphism. Here we don't do isomorphism. It's a branch-like events that's happening. So if they intersect at an event, that means a branch-like event happens that merge them, and they cannot intersect at an edge, I think, because each edge only has one creator event.
I see. Right. So they have to merge at an event.
Yeah.
Okay. So the criterion for causal invariance is probably that. Okay. So it's a little bit of a weird situation because what we're saying is they branch at an edge, they merge at an event.
I don't know. It's a weird kind of causal invariance because it doesn't mean it doesn't matter which order we apply these events. What it means is that the branches interfere with each other at some point.
Yeah. Well, what do you mean it doesn't matter? I mean, at some level, remember, if what we're trying to do is to reconstruct these anti-chains, it's not obvious to me that then, I mean, there's some theorems to prove about what matters when.
Yeah, the thing I confuse. Okay, so in the global multi-way system, the basic idea is that we can apply different rules, different events in different order, and we get the same outcome.
Mm-hmm.
Here we have this automatically for space-like events, which is not automatic in global multi-way system. But here it is. But for branch-like event, I don't think we have it at all. Because they would never merge in a trivial way.
Well, they can.
I mean, they can produce the same outcome. We just never notice it because we don't do isomorphism.
Yeah. See, that's, I mean, like Jonathan's interpretation of quantum mechanics, this completion-based thing, is basically saying, you know, look, the way to think about it is we too are these branching things. So we are not going to know the difference between, you know, for us, those things which are isomorphic, or maybe not globally isomorphic, but something analogous to that, will to us seem like a single thread of reality, if that makes sense. So the fact that, I mean, in other words, we are approximating that by asking for global isomorphism. And the true situation...
I think it's a different interpretation of quantum mechanics.
Which is?
Well, this one. Because we have a different way of getting branch interference.
Well, I mean, the classicalization of the whole thing is to say, look, the classicalization requires that there be a global, essentially, you know, causal invariance. It is forcing causal invariance in some way, and in the global multi-way system, it's forcing global causal invariance, right? But in fact, it's probably the case you don't need global causal invariance because you don't need to know, you know, your consciousness, so to speak, is only sensitive to a certain region of the multi-way graph. And while in principle, you might, if you waited long enough, you might be able to have global causal invariance. It's just not relevant, right? What's relevant is that the different paths that get followed in the local, in the thing that involves us, the edges that involve us, so to speak, that there be convergence there is what's important. Global convergence is not going to be that important. I mean, global convergence might happen, but it might take forever to happen. It doesn't matter.
Yeah.
So, right. So, I mean, the question here is, in what sense is there local? So I got two questions, actually. Okay, my first question is, if we look at this, is there any simpler system that we can look at? Is there anything that involves, I mean, the string rewrite system seems hopeless here, because your edges, it's just a different setup. This is the minimal system, I think, that has this setup.
Kind of. I mean, obviously, we can emulate strings of different systems and get what we get from that. But
yeah, I mean, you know, one thing I was just looking at last night, just from my intuition, was asynchronous cellular automata. Okay, so in other words, cellular automata where, because I know what they're supposed to do, right? And what's interesting is ordinary cellular automaton evolution is these maximal antichains. And you can get it with a foliation. In fact, you had, you know, we made a drawing of that. You made a drawing of this brick-like foliation that we did in the emulation of a cellular automaton by, you know, rewrite system. So, and I think that's the, but that foliation, by the way, notably, requires quiescence at infinity. In other words, that foliation is faster in the middle than it is at the edges. And at the edges, it has to kind of go quiescent. Okay, but I think what's going to be useful here. So first of all, obviously you should package what you have. This looks really wonderful, really good.
Well, yeah, I'm working on it.
But I would call this thing
edge event graph.
Yeah, edge event graph. Or is the convention with plural or not? Evolution events. I think it's called. I think it should be called edges events graph. I think that's the right name.
Okay, here's a list of all names I have. But there's edge count list, for instance.
Yeah, but there's event states list, which is exactly analogous to this. So what we want is
edges events graph.
Yeah, edges events graph. But then we want, in addition to that, so I think we want edges events graph, and what we've done in the multi-way case is we also need one where, I mean, there we call structure the thing where you don't show what the events are. Now here, is there any way to display in these events anything reasonable? Probably not. I mean, each event...
we can display edges, including the vertices in those edges.
Sure, but so what we could do is to take the whole global system. I mean, one thing we could display, which is the analog of what we had before, is the global system with something lit up.
But there is no global system.
Fair enough. Okay. Okay, so what do we display in the events? The events are just, I mean, they're very boring because every event is basically the same, right?
Yeah, pretty much. But it's the structure of the causal graph that is interesting.
Oh, I know.
What we're showing already.
So you also need something that says, that's called multi-way causal graph, right?
But it's just a causal graph.
No, it's not, because, well, how are you going to pick between, how are you going to pick between this multi-way evolution and the traditional,
Event selection function. I mean, causal graph has to return a graph. So in the multi-way case, it would either just return multi-way graph, which I think is the most reasonable thing to do, or it would return an error because it cannot return multiple graphs.
Ah, blah, 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 blah. Yes, fine.
What do you mean?
It's not useful, but yes, it should return the multi-way graph, not an error.
Right, okay. But because states list would return an error, because I don't know what else to do.
Yeah, that's fine.
I mean, it would return, I mean, it would work like in system like this, it would still return the normal.
I mean, just as a matter of syntactic sugar, we probably should make some of the common things, we should have it say multi-way blah, blah, blah. And when you ask for the multi-way blah, 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 it picks event selection function to none. Just as a matter of syntactic convenience.
Let's see, well, that.
What is global?
Okay, for Wolfram model, sure. But for Wolfram model evolution object is not going to work because it has no idea whether it's a multi-way system or not.
I see. All right.
So,
well, for now, just deal with the event selection function.
I think it would be confusing.
Yeah. Well, okay. For now, just deal with the event selection function. I suspect when this stuff gets included in multi-way system, then we'll have to think about this. Okay, fine. So just event selection function to none for now. Okay. So let's understand what you should do to package the finding of anti-chains. Do you see what I'm asking?
Well, so the plan is to return basically, well, let's see. Well, the C++ code should probably determine whether it's space-like or not, because it will be faster.
Mm-hmm.
And then it would probably return either this graph of space-like separation, as we talked about, or if you care about all of the separations, you just return the matrix. And then I want to try some approach clicks to determine basically, well, enumerate the clicks in some way. And make a function which would either be all states or independent states.
Okay, so hold on. Let's walk this through. Okay, so for every so what we want to do then, for every we want this matrix that says, I don't know whether, you know, for the matrix, let's see, it's an edge to edge, but also edge to event. So I'm not quite sure how to do that.
But it's not necessary, I think, because it's, I mean, if you know it for all edges, we can determine for events. Actually, it would be probably better to do it for matrix for events because it's smaller.
Yes. Okay, so for all events, we have a matrix that has basically, I mean, it's almost 0, 1, 2. For, I mean, that's literally, well, we could even do 1, 2, 3 for time-like, space-like, branch-like, because that's actually our ordering in the insofar as we have a metric on the space, that's basically how we're doing it. So I mean, that's a little bit of a hack, but it's okay.
Wait, what is ordering again?
I'm just saying 1, 2, 3. Time-like is 1, space-like is 2, branch-like is 3. Now, but each one could be pair, right? A pair of events could be both space-like and branch-like, right?
Well, yeah, so we could return a list for each entry in the matrix, but I think it's, well, it depends on what you want to do with it. If you just want to find independent states, you don't actually care about that.
Why?
Well, because you only care a space-like.
You claim space-like, you claim the ordering is time-like trumps space-like trumps branch-like. In other words, if there are two things that are time-like
No,
separated.
time-like trumps branch-like trumps space-like.
Wait a minute. If it's time-like separated, game is over. They're not.
Yeah, yeah.
Right?
And if they're branch-like separated, they can't be space-like separated.
I see. Okay, so you're saying that we treat it as branch-like separated. It's not clear that that's right to me, but I think we probably want both versions.
One reason to do that, well, yeah, we probably do want to return.
Actually, we want even another thing as well. We want to know how many steps back we had to go before we reached a common ancestor. Right? We need to know that information as well. We need to know how many steps back and what was that common ancestor. I mean, we could even just record the actual name of the common ancestor, right? Well, look, we could record.
Yeah, that would be better because that's enough to reconstruct.
Okay, so here's what we want to do. We want to have two lists, the common ancestor events and the common ancestor edges. For every pair of objects, we want to know the common ancestor event and the common ancestor, the list of common ancestors.
Generally, yes, I agree.
Because there could be multiple same distance. That what we do is we just say, go back a certain number of edges in the
well, we can return lists, but I think, well, the point is, this is going to be a very large data structure, so we shouldn't return everything by default. We should have, less data, more efficient versions of it.
Sorry, my mind wandered onto something completely different. Let me see. So
I was saying we probably want multiple versions of the data structure because we wouldn't always want to have the entire list of.
Yes, no, I agree. So I'm still a little bit. Let's think about your click concept. So the click is, see what surprises me about the click. This notion of a pure space, basically, which is what the click is. Something with no branch-like entanglements.
Right.
It just surprises me that this makes sense. In other words, it's like, wait a minute. You can clearly have two, that there's a minimal click and there's a maximal click. So in other words, there could be two clicks.
There's actually multiple maximum clicks as well.
Yes.
So if we enumerate all clicks, I suspect we are going to just get the states in the global multi-way system. Well, if we do space-like multi-way system, not non-multi-way system.
Yeah, but I'm trying to understand in terms of multi-space, what are the clicks? Right.
One layer.
Well, but they are routing through the towers. Remember, let's say you have 3 towers, right? Then all possible choices of which way you go through each tower will be a valid space-like slice.
Yeah.
Okay, but I'm not seeing how that's going to work with the clicks, because it should be the case then that there are 3 distinct clicks that can be generated.
Wait, why 3 clicks? You mean each click do you mean that clicks are space-like with respect to each other, but they're time-like or branch-like inside?
No, I mean that they're space-like inside. It's a click of space-like separated edges, okay? But I'm not understanding how that, okay, consider the case of the multi-space graph, okay? The multi-space graph, and can we draw the multi-space graph? Because the multi-space graph is a graph of elements connected. So in other words, we've got an edgewise, okay, so in this thing, we potentially have an edgewise space-like click. Right?
Can you explain again?
Okay, so we can have a space-like click that is objects that are pairwise space-like related, right?
Yeah.
You understand what that means? Okay.
Right.
So now imagine that we've got a bucket of edges that are all pairwise space-like separated.
Okay.
Okay. So then we can ask, what are the elements within those edges? Right? Because that's going to give us what we would normally draw in multi-space. What we want to draw is a bunch of elements.
Right.
And
so far you just described normal hypergraph.
No, I understand, but I'm trying to understand what the branch-like, because in multi-space, right, what's going to happen is that instead of there being a single choice of how those elements are knitted together by edges, well, okay, so one possibility is that in the towers in multi-space, what lives in those towers? Is it copies of edges, or is it just copies of elements? In other words, to represent look, once something is in a click, it's in a click, and you can't be partly in a click. I mean, it's either a click or it isn't a click. Is that right, or am I confused?
Well, in that same click, yeah. I mean, what?
Yes, I mean, that's what it means to be a complete graph with respect to those edges. So you can't be in 2 different clicks. Is that a true statement?
You can. For example, let's suppose we have almost a click, but with one edge missing.
Oh, I see. I see. So that's what's going to be the, okay. So in this multi-space, the different levels in these towers will correspond. So there'll be some way of creating. Okay, how do we get from the collection of space-like edges? How do we get the what am I trying to say? How do we get the thing that's our traditional hypergraph? We've got a collection of space-like edges. They have elements in them. We're looking at that bucket of, yeah, that's right. It's just those edges and they're knitted together by their elements. There's a bunch of relations knitted together by their elements. That's not problematic.
Yeah.
That makes sense, right? And that's the yeah. Well, great. When will you have this local multiway thing sort of ready to roll?
Well, without the states, probably fairly soon. But
Okay.
maybe beginning of the next week.
Okay.
So evolution, except for this aborting thing, which I need to investigate, evolution should be working fine already.
Great.
I mean, it's unit tested and everything.
Great.
So I just need to, but the reason it took me so long is because I actually did a bunch of refactoring, because previously the causal graph data structure was edge-based. So for each edge, it specified what creator and destroyer events are. Now it's events-based, which is better because, for example, it tells us in which order the inputs of an event were matched, which was not accessible before. But because it's refactoring, I basically need to rewrite all the properties in Wolfram evolution object.
Okay. All right, and then you will have a packlet update that does this. Is that the idea?
Yeah.
Okay. Wonderful. And it will be compatible with everything that we've done before, but it will just add features. Yes.
Yeah. So the API will be completely compatible. The ones in evolution so all the evolution objects. The plan is to make them convert automatically to new versions once they first encountered. So that should work as well.
Good. Okay. Okay. And great. And you should use our standard colorings for these things. I mean, I think that the only question in the edges for the edges events graph.
And the edges in the evolution states or evolution events graph?
Yes, they're the same. They're the same. Right, they're the same. Well, this is very beautiful. Very nice. I mean, I really like this way of this definition of space-like, these definitions of space-like, branch-like, etc. Very clean.
Yeah.
This is good. All right, listen, we actually had a different topic we were supposed to be talking about. Let me switch computers and then let's restart on our second topic.
Okay.
So let me just hold on. I'm gonna close down my part of the Zoom session. So and I will reconnect on a different computer in a moment. I need to get a cookie as well.